Hi there, on the bench today a donated vintage power supply from Germany. I think it was used for school physics lessons. It is cube shaped and for its size very heavy, about 8 kilos. On the left we have a variable DC output and on the right sockets for a fixed 6 volts AC and a variable AC. The big knob in the middle is to adjust the voltage. The front plate says the maximum current of either AC or DC is 10 amps and each has an overcurrent circuit breaker rated for 10 amps. The only other thing of note is the power input connector on the rear. This type is long obsolete, although there is still a company making a matching plug, but at outrageous prices. The only screws visible are those on the front plate, so let's take those out to see if I can get inside. The whole 8 kilos of gear are obviously mounted on the front plate, which makes taking it out not an easy job. It is beautifully wired, all carefully arranged in as straight lines as possible. As expected, a core part of this thing is a variac, but of equal size is that massive red thing, which is the rectifier. This is a Selenium rectifier in a single-phase full-bridge configuration. It is rated for 25 volts AC, producing 20 volts DC at up to 12 amps. Too bad there isn't a date code anywhere. Maybe that 65 in the drawing number means 1965? That would make sense, since these rectifiers were phased out in the 60s and 70s in favor of silicon diodes. Although for school equipment like this, they may have been used longer because they were pretty robust and could survive some abuse. To be able to use it, I removed the vintage mains input connector and replaced it with a modern IEC C14 type. The way it connects internally using this terminal block will stay the same, so I prepared my replacement to work with that. The IEC connector fits into the original hole, but the mounting holes have different spacing, which required a bit of tweaking before I could screw it down. The other end is now in the terminal block and I added some yellow-green earth sleeving to the wire that goes from there to the metal part of the variac. Now, with a proper input connector wired in, time to power it up. I'm going gently here, staying at less than half, mainly because Selenium rectifiers that haven't been used for a long time need to reformat themselves before they can start working again. The variable AC seems okay, and the fixed 6 volts as well. Now for the DC. Goes to 12 volts DC, so far so good. I decided to keep that running at this level with no load for at least a couple of hours. After that, I dared to conduct a few more experiments, still gently though, trying a 12 volt 20 watt light bulb as a load on the variable AC while measuring the voltage. No problems here, except the bulb falling off the table. But no harm done. Can I run the bulb on DC? It will be the first load current the rectifier has seen probably for years. It seems to work just fine. What current does it actually draw? I reconfigured the meter and it's about 1.33 amps. I hooked up an oscilloscope to see the waveform. It's what you expect from a full bridge rectifier with no smoothing cap. A 50 Hz sine curve where the negative part is flipped upwards to become a positive, so the resulting wave is now 100 Hz. Since positive and negative half waves use different diode pairs, the fact that the wave peaks appear to have the same height means all the diodes work equally good, or maybe equally not so good. To find out, I think I can proceed with some more serious load tests now that the rectifier had time to get back into working mode. Starting with full load tests, and for that I'm using the load resistor toaster from an earlier video. I temporarily put a rather noisy fan on top because this test will produce a lot of heat. Basically I want to know if the unit can deliver 10 amps or actually a bit more to see if the circuit breakers still work and roughly how long tripping a breaker takes. AC goes first. Here we go. I increase the voltage until the clamp meter reads about 12 amps. And now we wait for the breaker or magic smoke. After about 2 minutes the circuit breaker pops out and cuts the output. And after reducing the voltage back down and waiting a few seconds for the breaker to cool, I can push it back in. And yes, increasing the voltage slightly causes the current to flow again, so everything still works. For DC, I need a way to measure more than 10 amps for some time, which roots out standard multimeters. I could have used a DC clamp meter, but for a change I used a shunt resistor from a video long ago. This one produces 5 millivolts per 1 amp, which means at 10 amps the fluke should read 50 millivolts. The power supply is starting to make a lot of noise and vibrations, far more than it did in the AC load tests, which means, is it a rectifier? Maybe it's the 100 Hz load pulses instead of 50 Hz? Anyway, after some hesitation, let's go for it. Every millivolt above 50 is an extra 20 milliamp loads above 10 amps. So we have about 10.5 amps, but will that be enough to trigger the breaker? It's taking a long time. Let's add a bit more load, 10.6 amps. And finally the breaker pops. Wow, that was nerve-wracking. And yes, the wires are good warm from all that current. But I hope the breaker has cooled down. Yes, I can push it in and it stays in. And a brief increase in voltage shows everything's still working. Encouraged, now for the test that I'm most fearing, applying full voltage to the rectifier. You see, this unit was made when the mains voltage was nominally 220 volts, but now we are at 230 and it can go up to much higher. If you recall from the label, the rectifier was made for 25 volts AC input, at which it delivers 20 volts DC. As I crank the vary up as far as it will go, the AC voltage is now slightly above 31 volts because of the much higher mains voltage and of course because there's no load. The DC output is more than 28 volts. All of this is running the rectifier way over its specification, but when I'm going to use this power supply later, it's very likely that I run at max AC for extended periods. Hence the DC part must be able to handle it. After running it for more than 15 minutes at full voltage, I detected a slight whiff of some peculiar smell, not quite but similar to rotten eggs. This is what I feared. If selenium rectifiers fail, they produce a highly toxic gas called hydrogen selenide. If the breakdown is not catastrophic, a selenium rectifier may be able to self-heal by running it at a low voltage until the diode junction layer reforms, but as the overvoltage is something that will happen all the time, this is no use for me. Let's have a short explanation of what this rectifier is. A selenium diode is made of a steel carrier plate with an electrode on one side. Between the electrode and the steel plate, a junction of cadmium selenide and selenium is formed. This forms one diode. In our case, we have a full bridge rectifier and the plates and electrodes form 4 diodes arranged this way. The 2 outer plates are sleeved blue and are connected by a metal bar. This is the negative DC output. The other side of the outer plates have yellow sleeved connections and form the AC input. The middle connection is sleeved red and forms the positive DC output. It seems this arrangement and color scheme was somehow standardized because you see images of all kinds of selenium bridge rectifiers following the same pattern. If that arrangement puzzles you, maybe this helps. The pattern forms exactly the same good old full bridge rectifier that you know from countless schematics. Selenium diodes have a very limited reverse voltage limit, which is furthermore quite temperature dependent. The hotter it gets, the lower the breakdown voltage, and as it starts to conduct in the reverse direction, it drops a lot of voltage, which at the load current means more watts turned into heat, making it even hotter. It's a thermal runaway. The only way to increase the reverse voltage limit is to connect more diodes in series, so the reverse voltage is divided across more junctions. If one junction can block, say, 25 volts, then 2 in series can block 50 volts, and so on, which is why you see arrangements like the one on the right with stacks of plates, that is diodes in series rather than a single plate like my rectifier. Of course, that also adds to the forward voltage drop of each diode, so with stacks of 5 you probably lose 5 volts per stack, again converted into heat. I'm actually amazed about the 25 volt AC permitted by the label of my rectifier. 25 volts AC is more than 35 volts peak, so the diodes in my rectifier must be better than this generic datasheet suggests. But feeding it 31 volt AC equivalent to almost 48 volts peak was probably too much. To dismantle it, I had to break out serious tools. A socket wrench to loosen the nuts holding the wires, and removing the rectifier itself was another major undertaking. I put little markers on the wires so I know which one were for what. Yes, I could work that out from what's on the other end, but it's easier to just label them AC, AC, plus and minus while disconnecting them. I disconnected the metal bar that connects the negative sides and put a piece of paper in between. This way I can test each diode individually. From AC1 to plus in forward direction, about 0.2 volts, remember these are not silicon junctions. And nothing in reverse direction, this diode is okay. Same for AC2 to plus in forward direction, okay. And nothing in reverse, this diode is also okay. From AC1 in forward direction to -1, okay. And nothing in reverse, good. From AC2 in forward direction to -2, okay. But more than 1.8 volts in reverse. This diode is leaking now, and sadly this rectifier can't be used anymore. Especially not if it will be regularly exposed to overvoltage. I added 2 horizontal metal bars to the bracket where the old rectifier was. Each bar has 2 standoffs to which this heatsink will be mounted. I already put a hole with an M5 thread into the heatsink for mounting the rectifier. The rectifier is an 800 volts 35 amps type from the parts bin, which should be more than enough to handle the max 10 amps. The slight worry is whether it will survive a short circuit on the output before the circuit breaker trips. I think in that respect the Selenium rectifier with a relatively large internal resistance was more forgiving. For now I just go with this one. If it should die, I either upgrade it to 50 amps or add a 20 amp fuse in the DC output. The heatsink with the new rectifier is mounted. The existing solid core wiring would not stretch to the new rectifier, so I moved it to another thermal block and ran 4 wires to the rectifier from there, using the same color code as the original, yellow for AC, red and blue for DC. For the solid core wires, I tried as much as possible to keep it in the same straight as possible style as the original wiring. It may be worth highlighting this part, which is of course still all original. There's only one secondary winding. The separate 6 volts AC socket takes their feed from the top end of the winding. One connection is difficult to see and goes all the way to the end point of the windings, and the other to the tap you see here. When I move the slider, you can see that it goes over the connection point of the 6 volts. This offers some interesting possibilities, as we will see. But first, my reverse engineered schematic, which is simple enough. I show the voltages here as they are labeled on the front panel, although they are higher now because of the mains voltage is now higher than the historic 220 volts when this unit was made. A few points to mention. Notice that the DC output goes effectively through both breakers. I guess they did that so that the transformer is not overloaded if someone uses DC and the AC output simultaneously. If the feed to the rectifier would connect to the other side of the AC breaker, you could simultaneously draw 10 amps DC and 10 amps AC with the transformer glowing red without tripping a breaker. But nothing stops you from doing the same silly thing on the second AC output. You could draw 10 amps on the 6 volt socket and 10 amps on the variable socket without tripping the AC breaker. The nice red on light is an incandescent bulb connected directly to the 6 volts output. I show the 6 volts AC socket crossing over because that's how they are wired if you look from the front panel. Keep that in mind for the following. The left multimeter is connected with the black leads to the variable AC output, while the right one is connected with the yellow leads to the 6 volt AC, which is actually almost 7 volts. When I turn the knob to move the slider, the left meter changes while the right one does not, as expected. If I change the lower yellow lead to connect to the lower variable output, I now have 25 volts AC. And again, turning the knob only changes the left meter reading. Moving the upper yellow lead to the other 6 volt output, and now I have 32 volts AC fixed voltage. It is now connected to the full secondary winding. Moving the lower yellow lead one up from the bottom socket, and now I have a variable voltage that changes opposite from the left meter. It's 0 when the left meter shows 30 volts and 32 volts when the left meter shows 0. If I move the upper yellow lead to the top position, I have again a variable voltage going in the opposite direction of the left meter, but something interesting is going on when I move the knob to the right. In a close-up and after turning auto range off at the multimeter, you can see this effect clearly. The voltage drops to a minimum at about 21 on the outer scale of the knob and then increases again. Inside, the 0 point is where the slider crosses over the position of the tap point for the 6 volt output. Here are the 4 cases I just showed, using a simplified schematic where everything that doesn't matter has been removed. If you examine those, pause the video if necessary. I think it's pretty clear what's going on. The last case is probably the most interesting because moving the slider over the tap point produces a 180 degrees phase shift in the AC voltage. On the scope, the blue trace is channel 2 and corresponds to the yellow leads. Sorry, I did not think about color matching at the time of recording. The yellow trace is the normal variable AC output. Unfortunately, because both channels share the same ground, I have to pick the sockets connected to the slider as common ground, which is why the 2 traces are already appear 180 degrees out of phase. For the demonstration of the phase shift, it does not matter. As I turn the knob to the right, the amplitude of the yellow trace increases and the blue one drops. Only to increase again, but now with a 180 degrees phase shift. Now yellow peaks happen at the same time as blue peaks. If I turn back, you see that now yellow peaks happen at blue troughs. For comparison, this is the other case. And as explained, the waves appear 180 degrees out of phase because of the way the scope is wired into the setup. But as I turn the knob, the yellow and blue trace change amplitude in opposite directions, but their phase relationship does not change. After all this AC stuff, I'm sure you also want to see the new rectifier at full load of 10 amps DC, which is also an opportunity to try out a new electronic load that can handle such things. Here I'm ramping up the current remotely while capturing the data. I will make a separate video about this load. The washed out display is a camera problem. It appears totally fine for me in the room. We are at 10 amps now and the transformer gives an impressive hum, but overall the electronic load makes this test much quieter than in my previous setup. Whoops, the circuit breaker tripped, even though I was drawing only 10 amps and no more. Looking at the recording, a couple of interesting observations. Firstly, the voltage drops quite a bit over the test. Initially, the cause is mainly the AC transformer when it moves from idle with no current flow to getting loaded with more and more current. Then we get the forward voltage drop in the rectifier diodes, which gets larger as the current increases. Secondly, the voltage is wavy. It is of course transformed mains voltage, so any mains fluctuations affect the output, but I suspect that a bit of this waviness is caused by using no smoothing cap. If you recall from earlier, the output of a rectifier without caps is just 100 Hz pulsing DC, which is kind of sampled by the electronic load. And that is the clue to what's wrong with my test and why the circuit breaker tripped after just 75 seconds at the nominal load. This is not nice and steady DC. This is my RMS model spreadsheet from a previous video, which actually already contains a model of a full bridge rectified wave, the yellow trace. Ignore the others which are not relevant here. Check out that video, which also has a link to download the spreadsheet, which works in either Excel or LibreOffice. I set the peak to 8.05 simply so the model matches what I had arbitrarily set the transformer to. The model shows that a DC coupled meter will report about 5.07 volts DC, but the true RMS is higher, nearly 5.7 volts DC, and the RMS value is the one that counts in terms of heat produced and watts delivered. The mains voltage is fluctuating a bit, so bear with me that the values keep changing. Anyway, both meters show the predicted average DC of slightly above 5 volts. The red meter shows a significant AC component of more than 2.5 volts, which adds to the current and therefore needs to be considered. Therefore, I switch the red meter to show AC plus DC, and in doing this I get the RMS value predicted by the model. And here's the model for confirmation. DC 5.69 volts RMS versus 5.07 for just the DC component. The real waveform isn't quite as perfect sinusoidal, but close enough. The mains voltage had fluctuated a bit again, so the peak and RMS value on the scope are slightly higher, but essentially the same. This is voltage. Of course, the same is true for the current, and I should have measured AC plus DC current instead of just DC as I did before with the shunt resistor on the display of the electronic load. I considered and then rejected adding a smoothing capacitor to turn this into a nice and steady DC. For a 10 amp load current, such a capacitor would have to be enormous, and it would still not totally eliminate the AC part, called ripple in that case. And the capacitor would be highly stressed dealing with 10 amp of ripple current, significantly reducing its life. Before doing the new test, I decided to temporarily attach a temperature sensor which directly touches the rectifier. The sensor wire goes through one of the holes in the enclosure, allowing me to put the whole thing back into the box so the measurements reflect the actual operating conditions. I used my Fluke 187 to measure the current through the shunt, but set it to AC plus DC. At the moment it's just a tad below 50 millivolts, which would be 10 amps. The Bryman BM869S is reading the rectifier temperature. This is the beginning of the test, so it's still quite low but climbing steadily. Both meters are connected to a computer to record their measurements every second. The electronic load is reporting only 8.2 amps because it only knows about the DC part. The recording of this run. The transformer was set to maximum DC voltage output. The DC breaker tripped after about 29 minutes, which was probably a good thing because the temperature was 75 degrees Celsius or 167 degrees Fahrenheit and still going up. I suspect the DC breaker is tripping a bit early, but there's nothing I can do about it, and to be true, I don't see me measuring that kind of current for that long anyway. I was curious if the temperature would eventually reach an equilibrium, and so I did another run with a current set to 8 amps or 40 millivolts AC plus DC on the current shunt and watching the temperature closely. After more than an hour, I did observe that the temperature values no longer increased and turned the test off. The breaker did not trip. The inset shows that from 4000 seconds on, the temperature just fluctuated just shy of 75 degrees Celsius, but did not increase anymore. Finally, I wondered if the rectifier temperature would change if the AC voltage was set to a lower value, but the load current remained 8 amps. It's the same current, but before the DC output was delivering more than 140 watts, and now maybe 30. The answer is yes. The equilibrium was about 68 degrees Celsius, 7 degrees less, and it was reached much faster. This kind of surprised me, since the forward voltage drop of the diodes is the same and the current is the same. The rectifier losses should also be the same, regardless of input voltage. I suspect what comes to play here is that the transformer and therefore the inside of the enclosure itself is getting less hot. I thought originally that this would be a very short video. After all, this is really a very simple device. But from dying Selenium diodes to connection allowing phase shifts to the need to consider RMS on an output labeled DC, it kept me busy. I hope you found it interesting as well, and I'm looking forward as always to read your comments. If you like my videos, don't forget to like and subscribe, and maybe consider becoming a Patreon. That would really help this channel. The link's in the description. Thanks for watching.